Hi, I am Jessica Franz, and this will be my presentation for week 1. I selected to do chapter 1.5, problem number 2, and I will quickly read the problem and then we will get started. Number 2 is the number of bacteria in a culture grows at a rate that is proportional to the number present. After 10 hours, there were 5,000 bacteria present, and after 12 hours, there were 6,000 bacteria present. Determine the initial size of the culture and the doubling time of the population. So here we have chapter 1.5, problem number 2 written out. It is a bacteria growth rate problem, and the information we get from it is there are 5,000 bacteria at 10 hours and 6,000 at 12 hours, and we want to find the initial size of the culture and the doubling time of the population. So this is a Malthusian growth problem, so the equation we have to work with is this, and we will then do the multiplying by dt and dividing by p to get the p's on one side. That isn't technically correct, but works. So this will turn into 1 over p dp equals k dt. And then from there, to solve for p, we will take the integral of both sides. That isn't technically correct, but will get us to the right answer, which the integral of 1 over p is ln of the absolute value of p equals kt plus the constant c for both integrals. And then from here we will raise each side to e, and that will give us p equals e to the kt plus c, which can simplify to p equals c1 e to the kt, where c1 equals e to the c plus or minus. And so from there, in order to solve for c1, we will take p of time 0 will equal p naught, which is the initial population at 0 time, to equal c1 e to k. 0 e to the 0 is 1, so that leads to c1 just equal p naught. So our equation found is p of t equals p naught e to the k t. So that is what we will be using. And from the given information, we see that p of 10 equals 5,000 and p of 12 equals 6,000. So if we plug those into the equation we just found, we get 5,000 equals p naught e to the 10k, and 6,000 equals p naught e to the 12k. So in order to solve for k, we can divide these two equations. So we're left with 5,000 divided by 6,000 equals p naught e to the 10k over p naught e to the 12k, and 5,000 divided by 6,000 is 0.833, and the p naughts cancel out, so we're left with e to the 10k minus 12k because of the division, which is 0.833 equals e to the negative 2k. In order to solve for k, we will take the log of both sides and end with ln of 0.833 equals negative 2k. To solve for k, we will divide by negative 2, and we find that 0.09116 equals k. So now that we know k, we can solve for p naught. So if we use the 10-hour initial condition, we have 5,000 equals P naught e to the 0.09116 times the 10 hours that we knew from the problem. And we can solve for P naught would just be 5,000 divided by e to the 0.9116 equal P naught, and we will find that P naught is equal to 2009.388. So the initial population is about 2009. So now for the doubling time, the equation that we have for that is the time equals 1 over k ln of 2. So doubling time equals 1 over the 0.09116 that we found times ln of 2. So the doubling time is equal to 7.604. So doubling time is about 7.604 hours. And that is problem number 2 from chapter 1.5.